Hello class and thank you for watching. In video 6.1 exponential functions, we're going to define exponential functions. We're going to talk about how to graph those and how we apply those in real world scenarios. Let's begin by first defining an exponential function. So the exponential function, let me write that better. Here we go. With a base b is defined as the following. So f of x equals b to the power of x, where our b is going to be a positive constant that is not equal to 1. So it's going to be a number that is greater than 0, but not the number 1. So for examples, so let's say that f of x equals to 5 to the power of x. That's an example of an exponential function. Compare it to this. If it's x to the fifth power, that is not an exponential function because the exponent is the 5, and over here, the exponent is the variable, your input value. Another example of an exponential function would be if we had negative 5 to the x power. In this example, our base is a positive 5 to the exponent of x that is being multiplied by a negative, so it's causing a reflection. So this is an example of a reflection of this function there. Compare it to this function here. This is not an exponential function because the base, as indicated by the parentheses, is negative 5. So slight differences again between an example and non-examples of these exponential functions. So let's talk about a convenient base. Now the most convenient choice for a base is the natural irrational number e. So e is an approximated value that is approximately around to 2.71. Very similar to pi, it's irrational, so it can be written as a function, and this is referred to as the natural base. And the function that uses this as the natural base, so f of x equals e to the x power, is your natural exponential function. So let's look at some examples of how to approximate these type of functions. Well, with our decimals calculator, that simply requires us to get our base, like in this example 5, and raise it to the 2.8 power. So 5 to the second power is the concept that we're multiplying two factors of 5. So 0.8 is going to be a fraction of that. So we have two complete multiples of 5, and then we're multiplying 0.8 of that value there, which is going to be your radical value, an irrational part right there. So using our calculator, we can approximate this number to one decimal point and say it's 90.6. And we can even do it if our exponent is a negative value. So if we have 3, like in the next example, and we're going to raise that to the negative 1.3 power, that equals to approximately 0.20, what's going on here? 24. So that's the approximation. Now here's Euler's number, so the natural base e to the 1.1. We can just simply use on any calculator, or specifically on this one, on the decimals calculator, simply using the letter e from our letter pad. That automatically picks up as on the device as this value right there, and raising that to the 1.1 power is approximately 5, oops, not 11.1, 3.004. So we'll just estimate it to 3. We could also put a negative number up there, negative 0.18. That's 0.84. So this is how you approximate again with the calculator, because the bases are being raised to, again, decimal values or negative values, you can always use your calculator to evaluate that. Now, there is a key significance between having a positive exponent and a negative exponent. You'll notice that those values are less than 1 when our exponent is a negative. And the reason for that is from the negative exponent rule, that if I have a base and I raise it to a negative power, then that's going to become the reciprocal of that base raised to the positive power. So for example, if 3 is raised to the second power, which is 3 times 3, I know that that value is 9. 3 to the negative 2 power is simply going to give me the reciprocal of that answer. So if 3 to the positive second power is 9, then 3 to the negative second power, that's going to be 1 over 9 as a result. So let's talk about the characteristics of exponential functions. In this video, we're going to be focusing on how to graph the transformation of these things. So let's talk about the characteristics first of the parent function. So the domain of the function of f of x equals to any base to the power of x is always going to have a domain of all real numbers. Doesn't matter what the base is, your domain is always going to be all real numbers. And the range will be the values of y that are going to be greater than 0, strictly greater than 0, not equal to 0. And again, that's irrelevant on what the base is. So whether the base is a half or 5, 7, 1 over 7, these two things are always going to be true for this format there. Now the graph of all exponential functions that are again in this form, b to the x power, pass through the point of 0, 1. Because any value, any base to the 0 power always ends up equaling to 1. Therefore, the y-intercept is going to be the value of 1. So the graph crosses the y-axis at 1. So if you look at the graph down here, that means that this point right there will always end up being 0 and 1. As long as, again, our exponential function has now transformations, we're not doing anything, and we have, again, b to the power of x. Now, there are no x-intercepts, so this graph does not cross the x-axis. So that means that there's going to be a horizontal asymptote. We'll talk about that right now. Now, if b is greater than 1 and f of x is equal to b to the power of x, then this graph right there is going to go up. It goes up to the right and is a one-to-one function, or in other words, is invertible. Because it's always increasing. Now, the greater the value of b, the steeper again that increase is going to be. Now, exponential functions are invertible. They are one-to-one functions. So they have an inverse. So an inverse does exist. The graph of b to the x approaches but does not touch the x-axis like I mentioned earlier. There is no x-intercept. So that means that this axis here, y is equal to 0, is a horizontal asymptote. Algebraically, what this means is that the equation b to the x equals to 0 has no solution. Okay? So this equation will have no solution as a result. Now, another thing that's important about this, another key characteristics about these functions that are written in this format, y equals to b to the x power, is that because, again, this is exponential, if I make the input value equal to 1, then the output value is always going to be the base. So besides crossing the y-axis at 0, 1, there's also going to be a point where the x value is 1 and the y value for that is going to be whatever the base is. So if, for example, if y is equal to 5 to the x, then this point here is 0, 1, and this point right there would be 1, 5. If it was 7, then this would be 1, 7, and so on and so on. Now at the bottom of this page, I have a quick reference guide to the transformations involving exponential. Everything from your translations to your reflections, your vertical and horizontal dilations, and what the notation will look like. So you just have a quick reference to that and how it affects the graph and the horizontal isotope. Okay. Now we're going to be focusing on these transformations here, not the last two. So let's go in the next couple pages and talk about these transformations, beginning with reflections first. So let's begin with horizontal reflections. A horizontal reflection is going to be a reflection across the y-axis. Okay, and it looks like this. If I'm going to reflect something across the y-axis horizontally, the notation for that is b to the negative x power. Assuming again that the value of b is a number bigger than 1, a positive number bigger than 1. Okay, 2, 3, 4, and so on. It could also be written like this because b is going to be a positive number and a number bigger than 1. Then we could also have the reciprocal of b, so 1 over b, making that number smaller than 1, and that changes the exponent to a positive value. So whether you're given the equation in this notation or you're given the equation in this notation, they're going to both be a horizontal reflection of the original graph of b to the x power, which is going to be a reflection across the y-axis. So let's look at example 2, a and b, okay? In a, I have the original function of 2 to the x power, and on b, I want to get the reflection of that. So let's first look at what the original function looks like, okay? Well, just plugging in values, which is the easiest thing to do, if I replace the value of x, let me highlight the right thing, x with 0, so 2 to the 0 power, my answer is going to be 1. Because again, that's the property of raising anything to the 0 power. That always equals to a value of 1. Now if I raise 2 to the power of 1, well, that's only one factor of 2, so that answer will be 2. And finally, 2 to the second power means 2 times 2, and that answer is 4. Now to get a negative value, to negative number for the exponent, that's simply going to be the reciprocal of raising something to the positive exponent. So for example, let's say x is negative 2. So 2 is going to be raised to the second power. Well, since we know that's 2 to the positive power of 2, 2 to the positive 2 is equal to 4, then that means that the reciprocal of this, the opposite of that, is going to be the reciprocal of that value. So since 2 to the second power is 4, then that means that 2 to the negative second power will be 1 over 4 as a result. So this would be 1 over 4, and the same thing is going to be true with negative 1. This would be 1 over 2. Again, the reciprocal of that value there. So if we plot these points and graph it, the graph will look like this. So there is our graph of 2 to the power of x. Okay, so let's compare that now to example B. How does that compare? Well, the difference between here is that this is going to be a reflection because we have x to the 2 to the negative x. That's going to flip this across the y-axis. So here, these points are going to be on the opposite side. So 2 that has a y value of 4 is going to be on the other side. So at negative 2, this graph is going to have a y value of 4. And since at 1, it has a y value of 2, that means that at negative 1 is going to be flipped. So these points are simply going to be flipped across that line, and the graph is going to look like this. And remember, we have a horizontal isotope at y equals to 0, which again, I didn't move it. It just is the exact same position as normal. But this is what this is going to do. It's simply going to flip this graph upside from left to right. So instead of moving away from the horizontal isotope like it normally does, like this one does, it moves away from the horizontal isotope. Having a negative sign for the exponent is going to make the graph move towards the horizontal isotope. Assuming again that the value of b is a number bigger than 1, okay? So we just need to make sure that that number is bigger than 1. If it's not bigger than 1, then we'll just simply flip it, and depending on whether this changes from a positive to a negative, and following that rule, we'll determine again which direction the graph is going to be. So we always want to make sure that this value here is not a number less than 1. It is always a number greater than 1. So let's look at the next two examples of parts 2, C and D. So in C, we have the original function of f of x equals 5 to the power of x. So the y values for these respective x's will be the following: 1, 5, and 25. Having the exponent be negative would be the reciprocal, so 1 over 5. Since a positive exponent gives me 5, a negative exponent will give me 1 over 5. And then 2 does the exact same thing. Negative 2 will give me the reciprocal of this, so 1 over 25. So the graph right here will look like this. I can't plot 2 and 25, that goes off my grid here, but the general shape again is perfect. And again, simply focusing on these 2 points right here, this is what I really want to focus on, those 2 points. Those 2 points are good enough to plot, and just understanding that the general graph will look like that. So this is what the graph will look like. Now, if we compare that to letter D is the same base, but now our exponent is being multiplied by a negative, which is the same thing as saying that we have 1 over 5 to the positive x. So whether it's written like this or it's written like this is going to draw a reflection of this graph over here on the left across this line. So instead of moving away from the horizontal isotope, this graph is going to move towards the horizontal isotope. So we're going to cross the y-axis still at 0, 1, but the left side is going to be the side that starts up and goes down. So at negative 1, the y value would be positive 5. So we're simply flipping this point across the y-axis and putting it over here. And then the graph would just simply go down. I can't plot the other 2 points very well, so I'm just not going to plot them. But I have a point here. This point right here would be positive 1 and 1 over 5. And then the other point right here, that point right here in red, would be positive 2 and 1 over 25. But just with those 2 points right there, well, again, the graph, just drawing a sketch of this, the graph will look something like this. Okay, let's move on to vertical reflections. To reflect it across the x-axis, a vertical reflection, the notation is going to be negative b to the power x. So we multiply the base with the negative sign instead of the x. Or negative 1 times b to the x. And like I said, there's going to be a reflection across the x-axis, not y-axis. The x-axis, a vertical reflection. So let's look at an example of this from example 3a and b. So in 3a, we have the original function of 3 to the x. So let's talk about that first and what that's going to look like. Well, just like the other functions, it's going to go upwards. So it's going to cross the y-axis at 1, like all functions that have this format. It's going to cross or have a point at 1, 3, because the base is 3, so 1, 3. And again, those are the key points again they should always worry about. And then we have other points we can use. That's 2, 3 to the second power, that's going to equal to 9. So the reciprocals would be 3 to the negative 2 power, that would be 1 over 9. And then 3 to the negative 1 power would be 1 over 3. So 2 will have a y value of 9. I can plot that point. So again, the graph is moving away from the horizontal isotope, okay? But now let's look at the reflection. So on the reflection, we're going to reflect it across this line this time. We're going to reflect it across the x-axis. So this is the line of reflection because of this notation. So multiplying the base by the negative, flips it across this blue line. So we're still going to move away from the horizontal asymptote, but instead of moving away going upwards, we're going to move away going downwards. So we're going to flip these points and put it upside down. So the point, the y-intercept, is now going to be at 0, -1. And this point here and this one are going to also be below us. So instead of going up 3 at 1, we're going to go down 3. Instead of 2, 9 to -9. Because those y values, as you see right here, our y values are going to be multiplied by a negative number. So 0, then you make a table of x and y values for this. So at 0, we're going to have a point at -1, 1 have a point at -3, and that's 2 have a point at -9. So you see this notation multiplies all of my y values, or I'm sorry, these y values by a negative, making them all negative. So the graph is going to move away from the horizontal asymptote, but the negative sign simply makes it move away from below. So you see, the negative sign right here makes it move towards the horizontal asymptote. The negative sign right here keeps moving it away, but just across this blue line there. So let's look at this example. So in this next two examples on 3, C and D, here we're not going to do a new function. We're now going to simply get the reflection of 3x and with reflection across the y-axis. So this notation, the negative sign being right there, is going to reflect it across the y-axis. So this graph, instead of moving away from the horizontal asymptote, it's going to move it towards the horizontal asymptote. So we'll have our y-intercept at 0, 1. At -1, the y value will now be at 3, and at -2, the y value would be -3. So just like from the previous page, having in the x be negative will make the graph go downwards and move towards the horizontal asymptote. So that's what this graph is going to look like. Now, in example D, we have two negative signs. So we have a double reflection. We have a reflection not only across the y-axis, but this is going to be reflection across the x-axis. So if I look at the previous graph, this one right here, 3 to the -x, okay, ignore that right now. If I know this, I know that this is going to move towards the horizontal asymptote. So if I reflect this graph across the y-axis, I'm sorry, across the x-axis, across this line right here, that's going to make it go upside down. So we're still going to move towards the horizontal asymptote, okay, but it's going to do it from below because of that right there. So this negative sign right here is just simply putting the graph below the x-axis. So recap before we graph it. Whenever our base is raised to the power of x, as long as this number is bigger than 1, the graph is going to move away from the horizontal asymptote. Okay? But if we have a negative x there, again, assuming that this number is a number bigger than 1, if b is bigger than 1, then a negative x is going to make the graph move towards the horizontal asymptote. Multiplying those bases by a negative, like we did right here, puts the graph below the horizontal asymptote, and having it positive puts it above the horizontal asymptote. So in this example right here, since this is a negative, that means we're going to move towards the horizontal asymptote, and because of this negative sign, we're simply going to do it from below instead of from above, like we did on this example. So the graph of this thing is going to look like this. We're going to have a point at 1, -3, at -2, -9, and the graph is going to move towards the horizontal asymptote. So let me connect those points. Oh, our y-intercept is at 0, -1, and it's going to connect those points and keep that graph below this horizontal line because of that negative sign. So this is what the graph would look like if I was reflecting it not only across the y-axis, but also across the x-axis. Not only am I making it go towards the horizontal asymptote, but I'm doing it from underneath. So it will look like this. Okay, let's talk about translations now. So let's assume that f of x equals to b to the x, where the value of b is a number greater than 1. So again, our base is a positive number bigger than 1. If we're going to translate any of these functions left and right horizontally, the notation will be one of the following. B to the x plus h, or x minus h in the exponent. If it's plus, the graph is going to move to the left, and if it's minus, the graph is going to move to the right. That is not a typo. That is exactly how it moves. Like in the unit that we talked about transformations, the same rule applies here. Any horizontal slide, the operation indicates the opposite direction. So plus is a negative direction and minus is a positive direction. So the opposite. So for example, to graph, let's look at example 4a. To graph the function 2 to the x plus 3 power, the 3 is going to move the graph to the left 3 units. So if we focus on 2 to the x power, well, we know the y-intercept is at 0, 1, and because the base is 2, that means when x is equal to 1, the y value would be 2. Those 2 points will move 3 units to the right. So that means that if I have 2 to the x plus 3, moving those 2 points 3 units to the right will move this point to negative 3, 1, and will move this point to negative 2, 2. So let's see, let's count. So normally this graph crosses the y-axis at 0, 1. A horizontal shift of 3 units to the right, 1, 2, 3, would put that point right there. So let's plot the points at negative 3, 1, like I mentioned. That's exactly where that is. And now the other point. So normally, 2 to the x, we should have a point right here at 1, 2, moving that 1, 2, 3 units to the left. I said right earlier, I meant left, right here to the left, is going to plot it right there at negative 2, 2. So let's plot that point, negative 2, 2. Our horizontal asymptote did not change. That's going to stay in the same position right there. And connecting those two dots, again, with the general shape, will draw us an exponential function that looks like that. Now, key thing that I want you to pay attention to here is look what's happening to the y values, okay? The y values are now the x values, the x coordinates to these original points are now 3 units smaller. So 0 minus 3 is equal to negative 3, and 1 minus 3 is negative 2. So that's the coordinates again. For this point, those are 2 coordinates for this graph here. So connecting those 2 points again with an exponential curve will make the graph move up. And on the previous example, when I said move up, I meant like it's growing up. It's increasing. It's moving in this direction, like it's increasing like that. Okay, not like we're shifting it up. So let's look at the next example. In example B here, the plus 2 is going to move it in a positive direction. So we're going to move it to the right 2 units. So first think about what the x and y values would be for 5 to the x power. Well, the y-intercept would be at 0, 1. And because the base is 5, that means that when x is 1, the y value would be 1. So normally we have a point here and a point there. And those 2 points will connect again to draw the exponential, something like that. Well, this minus 2 is simply going to shift those points 2 units to the right. So 5x minus 2 will add 2 to this. So we're going to add 2 to that value, add 2 to that value there. So it's going to be 2, 1, and 3, 5. So plot the points 2, 1, and 3, 5. And you'll notice that those points are now 2 units to the right. 0, 1, 1, 2 is right there. 1, 5, 1, 2 is right there. We moved everything to the right. So the graph will look like this. The horizontal isotope again is still on the y-axis, on the x-axis at y is equal to 0, and the graph will look like this. Okay, so let's do this next two. So in this example again, our horizontal ice hasn't shifted because even if I move this to the left 1 unit, it's a horizontal line, so it doesn't look like it's been shifted 1 unit to the left. But the points that are going to be these points right here. 3x normally has a point on the y-axis at 0, 1, and it's also going to have a point at 1, 3. So let me plot those points. So those 2 points, because of this shift up here, because of this shift, they are going to move 1 unit to the right. So let me grab them and let me move them. I'm sorry, not to the right, to the left. To the left. I say the wrong direction. To the left. So I was going to move them both right there. So connecting those 2 points, again with my exponential curve, is going to look like that. So there you have it. And for the last example on this page, the -3 is going to shift the graph in a positive direction 3 units. So 4x, let me plot those points first. So 0, 1, and 1, 4. Right there. So this graph F is going to translate to these points here. It's going to translate this graph to the right 3 units. So if I grab these points here and simply move them 1, 2, and then 3, that's going to put them right there. So the graph will look like this. Now again, let's analyze the location of these 2 points. So the coordinates of those 2 points that I just plotted are at 3, 1. Notice that the y value is the same, but 0 plus 3 is 3, 1. And when I add 3 to this, that's going to make the x value 4, and the y value obviously doesn't change, it's 4, because all I'm doing is just, as you saw right now, I simply shifted the graph 3 units to the right. So those 2 coordinates 3 units to the right and landed them there. So there is the graph for this transformation of 4 to the x power. Okay, and I've left vertical translations for the end because those are also going to affect the horizontal isotope. So then first of all, the notation to shift something up or down will look like this. It's going to be our base with our exponent x plus some constant or minus some constant. Assuming again that the value of k is a positive number, okay? So if it's a positive number, we're adding again this positive number. The graph is going to go upwards and it's going to shift the graph k units in a positive direction, so up. And if it's minus, it's going to shift it in a negative direction, which is downwards. Now, another reason that I left this at the very end, like I mentioned earlier, is because it also affects the horizontal isotope. With these vertical shifts, the horizontal isotope is going to move from y is equal to 0 to whatever the k value is. So if I'm adding that k value, it's going to be, again, a positive direction. But if I'm subtracting it, that means that the k value is a negative value, so it's going to move it to a negative direction. So for example, let's look at example 5a here. Here, I want to draw the graph of this function here. So the -3 is going to shift this entire graph of 4x down 3 units. So that means that the horizontal isotope is going to be at y equals -3. Since it's normally right here at 0, this is going to move it down 3 units. So that would be here. So this is the location of our horizontal isotope, that line right there. Now, everything else obviously also moves down 3 units. So our y-intercept of 0, 1, which is here, and our other point 1, 4 because the base is 4 at 1, the y value would be 4, are also going to move down 4. I'm sorry, move down 3. So 1, 2, 3, and it's going to put them right there. So the graph will look like this. Very, very cool. See? And if we analyze again and look in more detail what's happening to the y coordinates, you're going to see that the y coordinates to the original location of these, of 4 to the x, are now just simply 3 units lower. So if I do 1 and I subtract 3, I see that the location is 0, negative 2. And when I do 4 and I subtract 3, that puts this point at 1, 1. You see, minus 3 is negative 2, and 4 minus 3 is 1. So very, very cool. How cool is that? So for this example, it's simply going to move it up because it's plus. That will move it up 2 units. So 3 to the x is going to move up 2 units. So starting with the horizontal isotope, our horizontal isotope will put you right there. Our point 0, 1. 0, 1 would move up 1, 2 units. So that will put it right here at 0, 3. And because the base is 3, that means that we have a point at 1, 3. So moving it up 2 units, moving that up 2 units, 1, 2, is going to put it right there at 1, 5. So this is what the graph of 3x plus 2 will look like. So let's just finish off the rest of this page for the last 2 examples. So here, for the first one for letter C, plus 1 is going to shift the graph up 1 unit. So that puts the y-intercept right here at 1. Our y-intercept would be at 0, 1 because it's going to shift up, 0, 2 because it's going to shift it from 0, 1 up 1 unit. And because the base is 2, 1, 2 is going to shift up 1 unit to 1, 3. So our graph will look like that. And for 5x minus 2, that's going to shift the graph 2 units down. So that's going to put the y-intercept here at negative 2. And our y-intercept of 0, 1, it's going to shift our horizontal isotope at negative 2. And the y-intercept now, the y-intercept is going to move down 2 units to that location of 0, negative 1. And at 1, the base is 5, so we would have a point normally at 1, 5. That's going to be moved down 2 units. So right here at 1, 1. Oh, sorry, 1, 5 is right there. Moving that down 2 units, 1, 2 would move it right there to 1, 3. Not 1, 1. So this is what the graph will look like. Okay, so that concludes the first part to exponential functions. I hope you found this video helpful. I appreciate you watching and I hope you have a great day. Goodbye.